The first unit in calculus usually looks at the limits of functions, and we're looking at limits as a mathematical property of functions. We will start in this video by actually just trying to understand what a limit of a function is and ask why do we look at limits. In the next few videos we will look at these elements more precisely. But we will start by looking at tangents of functions and velocity. Velocity being really the most natural example where we look at limits of functions. So imagine an object moving on one dimension, on a line, but it is moving as a function of time. So we have time here as our independent variable, and our dependent variable is distance. So it could be a person walking on a path, it could be a ball being thrown straight up in the air, or any other object. And let's imagine that the object starts moving in space and it follows this curve. Now, by looking at this curve, we can try and learn about how this object is moving. We know that at a time, say t1, we can measure using the curve at what distance the object is. So say d1. We can look at another point, say t2, and using the curve measure the new distance d2. Now, if we want to know how long it took the object to go from D1 to D2, the time it took the object to move is just T2 minus T1. So it's this amount of time down here in order to go from D1 to D2. So the distance is D2 minus D1. So we have the time from this point to this point and the distance, and that in using those two variables we can also measure the average velocity. So the average velocity is given by d2 minus d1 divided by t2 minus t1. So the distance divided by the time gives us the average velocity. Now, if we connect these 2 points, we get a straight line. This straight line is also called a secant, and the slope of the secant is exactly equal to the average velocity, because we know the slope of a straight line is just given by the difference in the y coordinates divided by the difference in the x coordinates. In this case, our t, our time, is our x coordinate, and d, the distance, is our y coordinate. So when we look at the average velocity of this object between these 2 points, let's emphasize them in red, it is given by the slope of the secant between these 2 points, right? And that's how we can measure the average velocity. Now, the average velocity is nice to know, but what if we want to know the exact velocity, the instantaneous velocity, say at this point P? Okay, what is the instantaneous velocity? Well, we define the instantaneous velocity as the slope at this point. But how do we know what the slope is in this point? Well, one way to get at this slope at this point is to try to take points T1 and T2 that get closer and closer to our time at P. So we're going to move T1 towards TP and T2 towards TP, and necessarily D2 and D1 will move towards whatever the value is at this point P, the distance. So That is one way to get to an instantaneous velocity, by taking the average velocity of points near it and slowly getting closer and closer to that point that we are interested in. So let's look at this a little bit closer. We'll make a slightly bigger curve so it's a little bit easier for us to look at this. So say we're looking at this point right here. Let's emphasize this in red again. And we're looking at what the instantaneous velocity is at this very point. Well, we can look at this point here and this point here and put a line through it and measure the slope, right, by taking the difference in distance and dividing by the difference in time. And from here we learn the average velocity. We'll symbolize the average with a line on top. We can get a little closer and look at this one, right? And here we have a new slope, which is a little bit closer maybe. So now we'll have delta d prime over delta t prime, where we're getting a little bit closer to our specific point that we're interested in. But what we really want is the slope right here. And the slope right here is given by a line that barely touches. It just touches the curve at this point. Okay? This line that touches the curve at that point is called the tangent line. And the slope of the tangent line is given as we take the limit of the slopes of these averages, right? These average slopes closer and closer to this point. And so in that respect, we're looking at the limit as delta d and delta t go closer and closer to our actual velocity, okay, at the point P. And to do that, we have to take our delta d to become smaller and smaller, as well as our delta t to get smaller. So we're taking averages that are getting closer and closer to the actual point. Now, in this curve, we don't have numbers, so we can't actually solve it. But let's look at an example where we can actually calculate this. So this example is an example of the quadratic function. So f of x here equals x squared. That's basically the curve that is drawn in this diagram. Now, if you look at it closely, you'll see that I've identified 6 points on the curve, and one of them is in red. That point is just the simple point 1, 1 right here. So when x equals 1, f of x equals 1 as well. And I can ask the question, what is the tangent slope at this point? So I would like the value of the slope of the line that is tangent exactly at that point. So in order to get that, I can calculate various average slopes of the different secants that are given by different points, and I've shown these in green here. So we have 1, 2, 3, 4, 5 different points here, and we can look, say, at the average change of rate between each point and the point that we're interested in, the 1, 1 point. We can look at the slopes of the secants. Okay, so we're looking at the slopes of the secant lines that are defined by these points and the point of interest. For instance, that line there. And in this table here, what you see is the various x and y's for various points. The ones in green are the ones that are actually on the diagram. And I've calculated already the slope, the average slope, when I calculate it between each one of these points and this point of interest here, x equals 1 and y equals 1. Now, if we look at these values, we can see, okay, we have 0.5 and the slope is 1.5. Then we get a little bit closer to 1 by going to 0.7, and our slope is 1.7. 0.9, and our slope now, as we're getting closer, gets larger to 1.9. There are a few more points here that I do not show on the diagram on the curve because it's just too messy. But as you can see that as we get closer to 1 in x, our secant slopes are getting closer and closer to the number 2. We can also look at the slopes of secant lines from above our x equals 1. So 1.25, 1.1. And here, again, we're getting closer and closer to 1. So we're going down. And the value of the average slope goes from 2.25 to 2.01. So the slopes of the secant lines, as we go towards x equals 1, the value of the slopes goes towards 2. And in that respect, we're looking at the limit of the function of the slope function of this function. So that in this case, this is what we were looking at. We can, of course, look at the limit of just the function f of x, but that's kind of intuitively very simple. The limit of f of x when x goes to 1 is just 1. What's more interesting is to look at something like the velocity or the rate of change, which in this case is not something that we can easily measure just by looking at the curve, but we can calculate the different averages and look at how these averages slowly converge to a specific number, which in this case is just 2. Now, does this always work? So it turns out that you can't always find a limit by taking closer and closer looks at the actual point. And we will look at an example like that in a future video. But for a lot of functions that we're interested in, we can look at these limits of slopes and limits of the functions themselves. And in the next few videos, we'll get deeper and deeper into these examples and into a more formal definition of what the limit of a function is.